Alright, so let's move to the next discussion, which is about divergence conditions. Now notice that when we used our Maxwell's equations, we actually used only the first two Maxwell's equations, we didn't touch the other two equations. So the actual question comes is, when I am doing this discretization in space and time, what happens to the other conditions? Are they being violated or are they being respected, right? So in particular, take an example of your one of these equations. So curl of H is equal to dd by dt. We are assuming j is equal to 0 for now, although it's not necessary. Now if I take, and let's also assume a charge free situation. So if I take a dot product on both sides, okay, del dot del cross H, so this would be equal to del dot d. What should the left hand side be? Left hand side is an identity in vector calculus, right? This is always 0, right? Implies, so I mean we will just write this equal to 0 over here. So what is that in terms of time, what does that tell us about divergence of D? Constant, right? So this implies that divergence of D is constant in time. Okay. So if it, for example, if it is 0 to begin with, it will continue to be 0. This has nothing to do with FDTD. This is what Maxwell's equations are telling me, right? But now let us see that the update equation that I have written. So does, question is this, does FDTD respect this? That's the question we are asking. Yes, the other equation will tell me what is the value of this del dot d, for example rho, right? But rho may or may not be a function, I mean may or may not be a function of time, that depends. But under these conditions, this is what Maxwell's equations is telling us, just take a divergence. So let's reflect on this divergence condition a little bit, and we want to find out what does FDTD tell us about this. So what, how will we get an answer to this? So first of all, this is a condition that is in continuous space, del dot d, right? So if I want to look at it in discretized space, then I have to think of these stencils and discretized versions of which variable d, right? So which of the two polarizations will be more interesting to answer this question, TM or TE? TE, because I will have access to EX and EY and I can evaluate this divergence in a way that is easy to interpret. Otherwise, in the case of your TM polarization, I will have to be looking at the Z axis, right. So let's see, what should we do about this? So del dot D, when you see del dot D, what does it remind you of? In which theorem of vector calculus comes to your mind? Divergence of a vector field. Gauss's theorem or divergence theorem, right. So divergence theorem, let us say in 2D, because we are in 2D now. What does it tell us? Divergence of D over dx dy, yeah, will be line integral of d dot n cap dl, right, outward flux of the divergence, right. So this is our divergence theorem in, so if this was region S, this is gamma around it. So that's going to be one nice way of calculating del dot d over some space, okay. And the right hand side now has become the outward flux of D, okay. So now let's draw a, grid. let's go back to our TE polarization, which had Ex Ey or dx dy, right? We can now, since we are working with divergence, let's just use d instead of e. I mean, since we are working with the displacement field. So what is the variable that I have here? Hz is here at the center, right? And the other two variables are Ex Ey or dx dy, one and the same. So this is my dx, this is my dy. This is the stencil that I have. Now I want to evaluate this divergence theorem in 2D over here. So for that I need a surface and a line enclosing it. So what might be a good way to do this? And remember, I want to in that be able to evaluate d dot n hat. Okay. So just to give you the physical interpretation over here, this is some region over here S, and this is my n hat. Right. So something like that is what I want. So what kind of a grid, what kind of a region S will be suitable now? So the left hand side is not going to help us very much. The right hand side is a line integral. So what kind of integration contour do you think of? So it should be, well, a square will be the most natural thing, and since I want to evaluate d dot n hat, so if I take my contour to be along the grid lines, will it help me? Supposing I take the blue box itself to be S, sorry, not blue, green box itself to be S, will it help me? Because what will happen to d dot n hat? Well, not exactly 0, because let us say at this point where dx is there, there is also a value of dy. Dy is not 0 over there, but I am not storing that variable over there. I will have to calculate it by interpolation. So there is an inaccuracy over there. If I wanted to directly calculate this at the point, that means at this place where I have dx, the normal vector should be which way? Along dx. Then when I go to dy, which way should the normal vector be? Preferably along dy, right? So what if I take now, think of extending this, there are going to be 4 adjacent grids, 4 E cells, right? What should I do? So let us call this value h1, okay. Now there is going to be a dy over here also, there is going to be a dx over here also. Okay. Now do you have a hint as to what? A square, right? So if I take it like this, okay, at each center there is going to be some value of magnetic field. Okay, H1, H2, H3, H4. Okay. Similarly, I should give some names to these dx's to distinguish them. So this dx which is going outward over here, I will call it dx plus. It is leaving this red box. This dx on the left hand side which is coming in, I will call it dx minus. This dy over here plus because it is going out, and dy minus because it is coming in. So we have managed to get this all, right. So now what happens to the right hand side? Let us evaluate d dot n hat dl. Okay. So let us start from where should we can start from, let us say h4 to h1, right. 4 to 1 is the first leg of this thing. We can assume that the value of dx is approximately constant over this, right. So what is the first term over here that I am writing? Dx plus multiplied by delta y, right. This is my x and this is my y. Okay. Next is plus dy plus delta x. Next is minus dx minus delta y. Next minus dy minus delta x. So now, now that that's done, we have not yet actually used much of the FDTD. FDTD was one of the main points, was linking time derivatives to space derivatives. So far we have not done that. Okay. So now let's see how do we evaluate, let's say, so which is the equation that we are trying to do? Curl of h dd by dt. This is what is going to help us, right? So this equation I can look at the x part and the y part. We have done this when we looked at the TE stencil, right? We had those update equations for Ex, Ey. Basically that's what is needed. So what is dx plus, if you look back at your notes, dot, right? That's the time derivative. So what was that equal to? Just look back at your notes. This should be proportional to del h by del y, correct? So you remember the mnemonic we had made, top minus bottom, right? So top minus bottom, this will give us what in terms of the variables? What is top? For dx plus, what is top? Which value of h? h1. Which value of h for bottom? h4 divided by delta y. Okay, next is dx dot minus top minus bottom, same thing over here, h2 minus h what 3 divided by delta y. Okay, next we come to, we have done the dx's, then we come to the dy plus. Okay, so dy plus will become, so this was top minus bottom, and for this is going to be left minus right. If you don't remember this, no problem, you can just go back to your notes and just derive the difference equation. So dy plus is left minus right. What does that become? h2 minus h1 divided by delta x. Dy minus dot will be left minus right, so that is h3 minus h4 divided by delta x, correct?
There will be a minus sign, so it will be h1 minus h2.
h1 minus, no, so we have taken that minus sign into account and therefore come up with this left minus right. That minus sign is absorbed. You can just go back and look at your notes. Fine. So finally, what am I wanting to look at? Not this equation, but the time derivative of this equation, right? So what I want is, I have put a time derivative on both sides of this equation, and that will therefore be equal to the time derivative of, right? So what did I do over here? I just did a del by del t on both sides. So if I take a del by del t over here on both sides, what will happen? The time derivative will come on top of each of these dx's, right? So this will become dx dot delta y plus dy plus delta x. The same expression, just with now time derivatives on it, right? Okay. Now, do I have these expressions with me? Yes, I have evaluated all of these, right? So now if I take this expression and combine it with this over here, what do I get? So, let us substitute the first one, dx dot, this was plus, right, dx dot plus multiplied by delta y. What do I get? Dx plus dot h1 minus h4. Next term, the delta y got cancelled, dy plus delta x, h2 minus h1. Next term, dx minus h2 minus h3, and finally last term is dy minus dot h3 minus h4, right. What is that equal to? What is it equal to? 0. Everything is very neatly cancelled off, right. So, implies that over this tiny cell, del by del t of remains 0. We cannot say that this is true at every point, because we are not evaluating these fields at every point, but we are evaluating over a finite grid. So, over this grid S which I have shown over here, it is clear that that the divergence of D does not change in time. Okay. So, we can say we got this for free, we did not do anything special. What was the key reason we got this for free? The design of this E cell. By staggering everything by half a grid, those finite and those taking finite difference as two-sided, right? Centered differences. That's how all this H1 got cancelled from another H1 from somewhere else, and so on. All the H's got cancelled over there. So, this divergence condition being satisfied, that the divergence remains constant with time, we are just getting this for free, right. So, this is one of the sort of elegant aspects of the FDTD E cell. Okay. For the TM case, how will we prove it?
Yeah, because there is only Ez involved.
Right. So, there we will have to take our S not in the xy plane, but we will have to take it in, let us say, the your zx plane or zy plane or something like that, right. Then I will have, but that again won't help me very much, because my E will be along the n hat, I mean sorry, perpendicular to n hat. So, the dot product will give me 0. Yeah, the other divergence condition will be easier in TM. Yeah. So, this is in the case of TE polarization, you could show that del divergence of D remains constant. In the TM polarization, we will be able to show that divergence of magnetic field remains conserved. Yeah, that's also true. Actually, yeah, in the TE case, sorry, in the TM case, Ez is what? Pointing. So, okay, let us say take the TM case. What is electric field? Only Ez, and what is it a function of? X, Y, Z hat. What is, I mean, if you want to be very precise, let us make this D. So, what is divergence of D? 0 automatically, nothing has to be done, because this is del by del Z of something which is not a function of Z. Right. So, this is the easier thing to do, but in TE you have to take this loop and direction over here. Here, curl of which quantity? Which is what we did, no? Curl of H, well, we use curl. Yes, the other divergence equation, which is what? Del dot H, right? That will automatically be satisfied here by the same logic, because Hz is a function of xy. So, del dot H is going to be 0. Okay, so in other words, I mean, what the sort of final line is that if divergence starts out as 0, my FDTD scheme guarantees that it remains 0 throughout the simulation. Okay, there is no accumulation of error on that account. Okay, so we, yeah, as I said, we just got it for free. Okay, so we'll close this discussion now, and next we'll look at numerical analysis of FDTD.